Welcome to MIG, a course taught at the University of South Florida. This tutorial discusses comparator interrupts with the Arduino at the example of the microphone. We will discuss condenser microphones and how to use comparator interrupts to detect analog voltage changes. Let's have a look at condenser microphones first. The microphone that comes with the Arduino kit is such a condenser microphone. This means that the sound is detected with a capacitor where one plate of this capacitor is a membrane. We see that here. So when the sound wave approaches the membrane, the air pressure changes here, and that presses the membrane towards the backplate, which forms the other electrode, or it sucks it away. What that means, because the capacitance depends on the distance between the two plates, the capacitance either shrinks or it gets larger when the membrane is pressed towards the backplate. At the same time, the battery charges these plates to a certain level, so there's a certain number of positive and negative charges on these plates. Now when the capacitance changes while the voltage is constant, then the number of charges has to change. And that can only happen by a current flowing from one plate to the other. And as this current is pushed through the resistor actually has a voltage that is proportional to that current. That is given by Ohm's law, right? The voltage here depends on the resistance times the current that goes through it. So all we have to do now is to read out the voltage across this resistor relative to ground. So what we do is, when we connect this to the Arduino, this point here is defined as ground. So this is connected to the Arduino ground. This here is the signal output, and then this here is connected to 5 volts on the Arduino board. We just saw that the microphone puts out a changing voltage depending on the sound level. So if we want to detect this with the Arduino, then we need to look out for a voltage change on a pin. Since we don't know when this change occurs, there are two ways to do it. One is to sit in the main loop and look very often if the voltage changes on an analog pin, and reading out analog pins takes a fairly long time. So this would waste a lot of time in the main loop that could be used for other things to do. A much better way to do it is to use an interrupt. So what we would like to achieve is that every time the microphone puts out a voltage that exceeds a certain voltage level, that an interrupt is being triggered, and we then respond to this interrupt with an interrupt service routine. Since the microphone puts out a non-digital signal, so it doesn't go from 0 to 5 or from 5 to 0 volts, but it is an analog voltage change of a variable magnitude, what we need is an interrupt that is being driven via comparing the microphone voltage against a reference voltage. The Arduino has a setup that allows that. This is called the comparator interrupt. So what happens in the comparator interrupt, essentially an op-amp is used where we input a reference voltage, and then we compare this reference voltage to the voltage that is being put out by the microphone. And you see here, if the microphone voltage is lower or it is higher, it will result in a 5 volt or 0 volt output of this op-amp. So this digital signal that depends on the comparison between microphone and reference voltage, this digital signal now can be used to trigger an interrupt, which then causes the execution of the interrupt service routine. So there is a specific interrupt vector that is associated with the comparator interrupt, and this is called analog comp vect, and this somewhat cryptic abbreviation that is defined in the Arduino library. So we can simply use this expression in the interrupt service routine. So to summarize, the great advantage of using this comparator interrupt is that we don't need to waste time in the main loop to look for a microphone event, while Here with the interrupt, the microphone event simply triggers the execution of the interrupt service routine whenever the microphone receives a sound pressure that exceeds a certain level that is essentially defined by the reference voltage. Here we see the comparator interrupt circuit in more detail. This is from the Atmega 328P datasheet. You can get it from the Atmel website. It's from chapter 22. This chapter gives all the information about the registers and which bits in which register have what function. So all these references that we see here, ACBG, ACD, etc., those are references to bits in registers that control this analog comparator setup. So here in the center we see the op amp that's used as comparator, and we have two inputs, positive and negative, and the positive input is the reference input. And so the voltage on the negative input is compared with the reference input, and depending on whether it's higher or lower, we get a higher or lower voltage at the output. And since there's no feedback in this op amp, it simply goes either to 0 or to 5 volts at the output, depending on what the comparison yields here, larger or smaller than the reference. All we have to do now is to feed in a reference voltage and then bring in the output voltage from the microphone, and then we can use this here to trigger an interrupt that every time when there's a sound event will make the program counter jump into the interrupt service routine. So for each of these inputs to the comparator we have several choices. For the reference voltage, we can either use a built-in reference, which is 1.1 volts. This could be set with this bit, ACBG. And if we don't want 1.1 volts, if we want to control the reference voltage, then we can switch that positive input to pin D6. And that simply means that the D6 pin is being repurposed at that moment to serve as input to the comparator. When it comes to the signal that is to be compared, so that would be the output from the microphone, we also have several choices. We could just feed it into D7 and select that as input, or we can put it through any of the analog input pins A0 to 5. But then we have to go through the multiplexer. We will actually use pin A2 to read out the microphone because it is convenient due to the design of the microphone breakout board to just stick that board on the headers of the analog input pins. Okay, so once the signal is in the comparator and we can compare it with the reference, then here we get the output from the comparator, and depending whether we're larger or smaller, it goes from 5 to 0 or from 0 to 5. And then we get an interrupt triggered. There's still one last hurdle that the signal needs to clear. This is this AND gate. So here the ACIE bit, that has the final control whether this interrupt is actually on or off. Right, so if this is 0, then the AND gate will always put out 0, and so the the signal won't make it to the rest of the circuitry in the Arduino. We can also select the type of event that should cause an interrupt. Right, we can select that the interrupt should be triggered when the signal goes from 5 to 0, or we can select that it goes from 0 to 5, or we can select that both is happening. So this is done with these bits ACIS1 and 0. So all we have to do now to use this comparator interrupt, and we have to select the right inputs, and we have to select the right interrupt method, and we turn on the interrupt, and then we can use it. And so this is done by setting these bits in those registers. And we will see in the Arduino Sketch how this is done. Unfortunately, there are no dedicated functions like for the pin-based interrupts or the timer-based interrupts that are part of the Arduino IDE, or some convenient libraries that one can load in. That means we have to deal directly with these registers, but it's actually not so difficult. Okay, now it's time to look at the Arduino setup. As I just said, we directly stick the breakout board of the microphone that has these 3 output pins. We stick that directly into the headers of the Arduino. And so since we need an input pin for the comparator interrupt, it is convenient to just stick it here on A0, A1 and A2. And so A2, that is the output of the microphone, pin S on the breakout board. So this is the pin that we will then connect to the comparator through the multiplexer. The other 2 pins, A0 and A1, they just supply this microphone with power. So we will simply set pin A0 to 0. We will use them as digital pins. A0 will be 0 volts and A1 we set to high, so it outputs, and as output, both pins are outputs, we set to 5 volts, and so we have a convenient power supply next to the pin that reads out the microphone, so we don't have to use any jumper wires. So the setup here, that generates the reference voltage. The microphone puts out a constant voltage that is then changed by whatever sound hits the microphone, so we need to adjust the reference voltage to a voltage that's a little bit higher, so that we can detect sound events that push the voltage on pin S above its constant value when there is no sound. The reference voltage is generated by using a pulse width modulated signal that is coming out of pin 3. Right, all the pins that have a tilde that can be used for pulse width modulated output signals. And this output, this pulse width modulated signal, we feed through this filter, which is composed of the 10K resistor and the 10 microfarad capacitor into pin 6, which is connected to the reference input of the comparator. If this is a mystery to you, then I would recommend to watch the Arduino hardware tutorial video that is also posted on makecourse.com. Please note that it is important to put this capacitor in with the right polarity, so make sure that the negative pole, which is indicated by that ribbon with minus signs on it, that is connected to the ground pin or header, while the positive side of this capacitor is connected to pin 6 together with the pin of the resistor. Here you see the setup in the flash. On this side, this is the setup for the reference voltage. So here we have the resistor and this is the capacitor. Over here, the breakout board of the microphone is put into the analog pins A0, A1 and A2. What you also see are 2 oscilloscope probes hooked up, this here to the reference voltage and this here to the microphone voltage. When I demonstrate the sketch in action later on, then we will see this here as yellow trace and this here as the blue trace on the oscilloscope. So you can see how this signal occasionally goes higher than the reference voltage, and then the interrupt service routine is triggered and we get a report of the event on the serial port. This here is the ground connection to the oscilloscope. Here's a detailed shot of the breakout board. And this is the filter setup. So we have the capacitor connected between ground and pin 6. Again, make sure that the negative end of the capacitor is on the ground side. And then we connect the pulse width modulated signal that's coming from pin 3 through the resistor into pin 6. And so these two here make a filter that then produces a constant DC voltage on pin 6. whose magnitude is proportional to the width of the pulse that is coming out of pin 3. Now it is time to discuss the Arduino Sketch. As usual, we start out with some definitions. Here we define the pin numbers of the Arduino and their functions. So the reference voltage pin is number 3. That's the pin that is being used to generate the pulse width modulated signal that then filtered yields the DC reference voltage for the comparison. Then we define the microphone pins, which are 14, 15, and 16. So they double as A0, A1, and A2. Pin 14 and 15 are outputs to be used as ground and 5-volt supply for the microphone. And pin 16, that will be used as input for the microphone signal, which will be fed into the comparator to be compared with the voltage that's being generated on pin 3 and fed into pin 6. Then we define a threshold value of 150. So this is essentially the reference voltage on a scale from 0 to 255, because the pulse width modulation is defined from 0 to 255. So it's just 1 byte. So 0 corresponds to 0 volts and 255 to 5 volts in this scheme. Now the microphone puts out a level of 105 on this scale, so you see that the threshold we select, the reference voltage, is 150, so it's a little bit higher. So when we have a sound event, then the microphone level will go higher than 105, and at a certain level of sound it will exceed 150, and that will then trigger the interrupt service routine. Here we define two convenient commands. So there are CBI, clear bit, and set bit, SBI, and all we have to do if we want to deal with these registers for the interrupt, for the comparator interrupt, we write the register name in here and the bit name in here, and then we can clear or set these bits, set them to 0 or to 1. Next, we define a couple variables that are being used in the interrupt service routine, the ISR, and as said before, they need to be volatile. So we have sound 0, that's used as a flag for a sound event that happened. So when this goes 1, then the sound event has occurred. And we have the second variable here, sound time, that stores the time at which the event occurred. Okay, now we go into the setup function. We start out with opening the serial communication at 9600 baud. Then we define the microphone pins, right? So 14 and 15 as outputs and 16 as input. We set the outputs to low and high to provide power, and the input will further down here will be connected through the multiplexer to the comparator. Here we define the reference voltage pin, so this number 3 as output, and we write in with analog right now. So this essentially defines a pulse width modulated output signal on this pin, and we write in so this is the pin number and then this threshold value that we defined up there. And so together with the filter, this will produce a certain voltage on pin 6 that's fed into pin 6. Okay, so down here, this is the complicated part of this sketch. These cryptic commands here, they will now set all these bits in the registers. So we have the ADCSRB register and the ADMAX register. So here essentially we set the multiplexer that A2 is being fed through it. And here we turn the ADC off, which usually is connected to the multiplexer. Now if you want to use it for the comparator, you have to turn it off. So there is this register, ADCSRA, and we need to set or to clear bit the bit that's called ADEN. Let's have a look at the Atmega datasheet real quick, so you get an idea how to deal with these registers and bits. So this is the analog comparator chapter number 22. This is a really big data sheet, a few hundred pages. So chapter 22, a few pages about what we just were discussing. So the first thing you see is the block diagram for the analog comparator that I discussed. And then we can go on to the discussion of these registers. And so here you see the ADCSRB register. And for example, here we need to enable the multiplexer for the comparator, and that so here we need to write in a 1 in the ACME bit. So you see here the ACME bit has this name, so it's bit number 6 in register ADCSRB. And so the convenient thing by using the SBI and CBI functions is we can just use this name and then say set or clear and exactly do what they suggest here, and then it usually works. So it's a very convenient way to deal with these somewhat cryptic bit names and register names. So just by reading the data sheet, they basically tell you here what to set to 1 and to 0, etc. Okay, back to the Arduino Sketch. Here we set the here we use a little bit of different syntax because we need to set the entire ACSR register to define all the comparator functions. We don't need to use these here, which only affect 1 bit. So here we can directly use the bit names and then or in zeros or ones into this register. So we set zeros and ones to these bit positions in the registers. Okay, so essentially what we define here is that we want to use the analog comparator interrupt, and the most important part here is probably down here, that's where we define the analog comparator interrupt mode. And we set it to toggle, so this means that the interrupt is being triggered no matter whether the voltage goes above or below the comparator value. So we will always catch the event after the microphone signal exceeds the reference voltage. Okay, now we go into the main loop. Oh no, first we should maybe talk about the interrupt service routine. This is down here. So here you see this interrupt service routine vector that is associated with the comparator interrupt. It's called analog comp vect. So every time the comparator interrupt is triggered, we jump into this routine, and all we have to do, or all we need to do here, is to remember the time at which it happens. So we read out the millis function, which gives us the time in milliseconds since the Arduino was turned on, and then we set that flag that indicates that some sound was detected. So this is all we do. This is a very short interrupt service routine, and now in the main loop we use this flag to detect whether sound happened. So we just ask here if sound flag is 1, then we carry out all these commands here. If not, if it's 0, then we just do the main loop without doing anything. And so in here now, after we detect a sound, we essentially store the time since last sound by calculating the difference between the sound time of the current event minus the sound time of the previous event, and then we store the current sound time as the previous sound time for the next time we come into this if statement. And then we print the time since the last sound that we just calculated divided by 1000, because it's in milliseconds and humans think in seconds, so we divide it by 1000 and then get an expression in seconds, and we add seconds to it. And so we print this on the serial port, and then we have a delay of 100 milliseconds because these sound events, because the microphone has a little bit of resonance every time it triggers a sound event. So in reality, several events are being triggered for each of the claps or whatever you want to detect with the microphone. So we wait for 100 milliseconds before the the mechanism goes active again. This could be done much better without this delay wait, right? You could do something useful in the loop and wouldn't just have to sit here in the delay function. Check the in-class project video that is posted where we deal with switches as input devices. So there is explained how to do a better debounce mechanism. Okay, so after we wait, then we reset the sound flag, and so this basically makes the loop run again without going into these commands, and we simply sit now here and wait until the next time the interrupt service routine is being triggered, and then we print the next time that's defined as the time since the last event. And that's about it. Now it is time to see the sketch in action. So what we will do now is we will look at the oscilloscope and observe what happens there while I clap my hands. And on the oscilloscope we will see in blue the reference voltage, which is of course constant throughout the experiment, and then we will observe in yellow. The yellow trace will show us what's coming out of the microphone at pin S. And at the same time, we will look at the serial monitor and see what is printed. And so what you will see is that as soon as the voltage that's coming out of S exceeds the voltage that we have at the reference pin, then we will get the time since the last clap printed on the serial port. Okay, let's do it. Okay, it seems this was working. So this concludes our tutorial about comparator interrupts with the Arduino. Thanks for watching.